Hello everyone, my name is Nana and I'm from the Puthi Academy. So today we'll see about the chapter that is structure of atom. So till now we have seen about the atomic models, right? Various atomic models. Now what are those models? First one was given by J.J. Thomson. Then we have found that his J.J. Thomson's model, atomic model, wasn't able to explain certain things. Then Rutherford gave his model. It was again proved that Rutherford's model wasn't able to explain certain materials or certain concepts, which gave rise to the Bohr's model. Bohr's model could explain the things which Thomson and Rutherford can't, but there are certain other points which were not been explained by Bohr's model, and that led to the ultimate model which we use now, that is the quantum mechanical model. So this failures of these models gave rise to the quantum mechanical model of atom. Now let's see what is the quantum mechanical model of atom. Now, quantum mechanic model of atom. So a classical mechanics based on Newton's law of motion successfully describes the motion of all macroscopic objects such as falling stone, orbiting planets, etc. Right? Newton's, because of his theory, we can explain the falling of objects, orbiting planets, etc. Right? So which have essentially a particle-like behavior as shown in the previous section. Now, however, it fails when applied to microscopic objects like electrons, atoms, and molecules. Now, Newton's law of motion can be applied to microscopic objects. Microscopic objects means the ones which we can see, but the ones that are microscopic objects like electrons, atoms, and molecules, it wasn't able to explain its law with respect to this molecules or atoms. This is mainly because of the fact that classical mechanics ignores the concept of dual behavior of matter. This is basically because all the thing, okay, Newton's law, everything, they doesn't consider the dual behavior of matter, especially for the subatomic particles, because those are so small we can't able to see them, and the uncertainty principle is also ignored. So the branch of science that takes into account this dual behavior of matter is called quantum mechanics. Now, later, it was found an essential need to prove all these concepts, and the branch of science that deals with all these concepts is the quantum mechanics. Okay, now, quantum mechanics is a theoretical science that deals with the study of motions of microscopic objects that have both observable wave-like and particle-like properties. Now, quantum mechanics is a theoretical science. Theoretical means it deals with all the and theoretical part of the motion of microscopic objects like electrons, protons, neutrons, atoms, molecules. Those are all microscopic objects, right? So their movement is observed in both wave-like and particle-like properties, along with their wave-like and particle-like properties. So it specifies the law of motion that these objects obey. Now you know law of motion for all the macroscopic objects. Macroscopic objects means the ones you can see, the ball, stone, planets, even though you can't see just like that, but you know at least how they are orbiting and all. So this quantum mechanics, it deals with the movement, their positioning and everything with respect to the microscopic objects, and they state the law of motion of these objects. Okay, when quantum mechanics is applied to macroscopic objects for which wave-like properties are insignificant, the results are the same as those from the classical mechanics. Now, when they applied this law, quantum mechanics laws, to the macroscopic, that is the ones which we can see. The results were same as the classical mechanics. What they earlier got, results were similar for them. Quantum mechanics, it was developed by two scientists, Werner Heisenberg and Erwin Schrödinger. These were the two scientists who mainly worked on the quantum mechanics and developed it. Now, however, we shall be discussing the quantum mechanics, which is based on the ideas of wave motion. Now, in here, we will only discuss the quantum mechanics on the basis of which, on the basis of wave motion. Now, the fundamental equation of quantum mechanics was developed by Schrödinger. So, the equation which we use for quantum mechanics, that equation was developed by Schrödinger, and it won him a Nobel Prize in Physics in 1933. Okay, so the equation was which incorporates wave particle duality of matter as proposed by de Broglie. It's quite complex and knowledge of higher mathematics is needed to solve it. Now, as I told you, de Broglie is the one who gave that concept, right? Dual wave particle duality. Now, that was experimentally and calculation via calculation was proved by Schrödinger. He developed a new quantum mechanics का system. Now, that you will learn in your higher classes. So, for a system such as an atom or a molecule whose energy does not change with time, the Schrödinger equation is written as H psi E where H, it is delta H, okay, where delta H is the mathematical operator called Hamiltonian. So this is something related to maths. So this H, it stands for Hamiltonian. Okay. Now Schrödinger gave a recipe of constructing this operator from the expression for total energy of the system. Now he devised this operator from an expression, and he gave for the total energy of the system. Okay, now the total energy of the system takes into account the kinetic energy of all the subatomic particles, electrons, nuclei, everything. The total energy of a system. Now, if this is a system, the total energy of this system consists of the kinetic energy. Kinetic energy means the energy while created while moving, right? The kinetic energy of the electrons as well as the nuclear. Nuclei contains what? Nuclei contains protons plus neutrons, right? So, in short, we call them as nuclei. Attractive potential between the electrons and nuclei and repulsive potential among the electrons and nuclei individually. Now, what he calculated is, he calculated the attractive potential. How, what is the attractive force between the nuclei and the electron, and what is their repulsive force, repulsive potential among the electrons and nuclei, and he did it individually. Solution of this equation gives E and psi. Now this symbol is for psi. Okay. Now hydrogen atom and the Schrödinger equation. Now we'll see the Schrödinger equation on the basis of hydrogen atom. Now, when Schrödinger equation is solved for hydrogen atom, okay, the solution gives the possible energy levels the electron can occupy and the corresponding wave functions of electron associated with each energy level. Now, when Schrödinger's equation was applied for hydrogen atom, the solution gave possible energy levels the electron can occupy. There are energy levels, like various energy levels. Now, applying Schrödinger equation on hydrogen atom, it gave a result, it gave a solution where you can know the possible energy levels the electrons can occupy and corresponding wave function of them. Okay, and even the energy associated with the levels. So this quantized energy states and corresponding wave function, which are characterized by a set of three quantum numbers. Now, these quantized energy states, okay, these are known as quantized energy states. These quantized energy states, they are and corresponding wave function which are characterized by a set of three quantum numbers. Now these are characterized by a set of three quantum numbers. One is principal quantum number, that is n. Another one is azimuthal quantum number, that is L, and a magnetic quantum number, that is Mi. Okay, these are the three quantum numbers on the basis the energy states are quantized, arise as a natural consequences in the solution of the Schrödinger equation, and these arise due to the Schrödinger equation. Now, when an electron is in energy state, the wave function corresponding to the energy state contains all information about the electrons. So, whenever an electron is in an energy state, the wave function corresponding to that energy state contains the information about your electrons. And the wave function is a mathematical function whose value depends upon the coordinates of the electron in the atom and does not carry any physical meaning. This part is not important. Wave functions of hydrogen or hydrogen-like species with one electron, okay, are called atomic orbitals. Such wave function pertaining to one electron species are called one electron system. When the wave function or the atomic orbitals with one electron species are called as one electron system. Mostly hydrogen is the one. Or when helium, lithium, beryllium shows their oxidation states, they can be also considered to be one electron system. Now, the probability of finding an electron at a point within an atom is proportional to the psi square at that point. Okay, now psi is the wave function. Okay, psi is your wave function. Now the probability of finding an electron within an atom is proportional to psi square of this at that point. Now, the quantum mechanical results of hydrogen atoms successfully predict all the aspects of the hydrogen atom spectrum, including some phenomena that could not be explained by Bohr's model. So here quantum mechanics, whatever results we get from the hydrogen atoms, successfully predict all the aspects of hydrogen atom, which Bohr's model wasn't able to explain. Okay. Now, what are the applications of Schrödinger equation? Application of Schrödinger equation to a multi-electron atoms. Now, hydrogen is a single electron atom, right? What if I apply it to a multi-electron atoms? Presents a difficulty, right? So the Schrödinger equation cannot be solved exactly for multi-electron atoms. This difficulty can be overcome by using approximate methods. Now, as for hydrogen, it is just one electron system, right? So you can directly calculate all the things. But for other multi-electron atom, it is rather difficult to calculate. At that time, we take an approximate method. Such calculation with the aid of modern computers show that orbits in atoms and then and other than hydrogen do not differ in any radical way from the hydrogen orbitals discussed above. Now, such calculation, where we calculate it in approximate made methods aid to a modern computers, show that orbitals in atoms other than hydrogen do not differ in any radical way from the hydrogen orbitals discussed above. So the orbits are same for everyone. We're just adding an extra one. Okay. So the principal difference lies in the consequences of increased nuclear charge. Now you can see that orbits, they are not close to each other. There is a gap in between them. No, now, this gap is because of the increased nuclear charge. Because of all these orbitals are somewhat contracted, so there will be a push and pull with the electrons and the nucleus, right? That will lead to their difference or the size difference in the orbits or the gap between the orbits. This is basic mainly because of the increased nuclear charge. Okay. Further, unlike orbitals of hydrogen or hydrogen-like species whose energy depend only on quantum number n, the energies of the orbitals of multi-electron atoms depend on quantum numbers n and l. Now, the quantum numbers that are the principal quantum number, azimuthal quantum number, and magnetic quantum numbers. For hydrogen, it only depends on principal quantum number because it has only one electron. So it depends on principal quantum number. But for multi-electrons, the atom, it basically depends on two things. One is the principal quantum number and the other one is azimuthal quantum number. Okay. Now, there are different ways to calculate this numbers. Okay. Next is the orbital quantum numbers. Orbitals and quantum numbers. Now we'll see about the orbits, how the orbits are shared and how to calculate those orbits. A large number of orbitals are possible in an atom. Qualitatively, these orbitals can be distinguished by their size, shape, and orientation. An orbital of smaller size means there is more chance of finding an electron near the nucleus. Now, there are large number of orbitals possible in an atom because as the number of electrons increases, there should be increase in orbits also because we have to keep them within the atom, right? So the qualitatively these orbitals can be distinguished by their size, shape, and orientation. We can distinguish them with their size, shape, and orientation, how they orient. Now, an orbital of smaller size means there is more chance of finding an electron near to the nucleus in case of hydrogen because there is only one electron. So there is a possibility that you can find the electron near to the nucleus. Similarly, shape and orientation means that there is more probability of finding the electron among certain directions and along others also. Now, shape and orientation means you can find it anywhere in the orbit, in any position, in any direction. Because atomic orbitals are precisely distinguished by what are known as quantum numbers. Now, these orbitals are distinguished or separated by the quantum numbers. So each orbital is designated by the three quantum numbers, that is principal, azimuthal, and magnetic quantum numbers. Now first one is the principal quantum number, that is denoted as n. Is a positive integer value. N is equal to 1, 2, 3, 4, just integer numbers. So the principal quantum number determines the size and to large extent the energy of the orbitals. Now what does this principal quantum number determines? It determines the size. What will be the size of the atom and to a large extent the energy of the orbital. What will be the energy of that orbital and the size? For hydrogen atom and hydrogen like species, energy and size of the orbitals only on n. Now, for hydrogen and hydrogen like species, as I told you, He plus, Li2 plus, in all these three cases, the size and orbitals depends upon only the principal quantum number. Why? Because all these three molecules are single electron molecules. They have only one electron with them. So that's why you only require principal quantum number to determine their size and the orbitals. Now the principal quantum number also identifies the shell. Now what is a shell? With the increase in the value of n, the number of allowed orbitals increase and are given by n square. All the orbitals of given value of n constitute a single shell of an atom and are represented by the following letters. Now shell means, now if this is the nucleus, around the nucleus these are the orbits. These orbits has various concentric circles in them. Those are known as shells. Okay, so there is K, L, M, N shells. So these orbits, these are known as shells. Okay, this is K, this is L, this is M, then N, and so on. Okay, these are shells. Now, the increase and the number of orbitals increases and are given when the number of orbitals increases, it is given as n raised to 2. So all the orbitals of the given value of n constitute a single shell of atom and are represented by, so this n, when it is 1, 2, 3, it will, the shells will be K, L, M, N with respectively. Whatever number, whatever alphabet you will get. The size of an orbital increases with increase of principal quantum number. And the size of an orbit, it increases as you increase the principal quantum number. Now, in other words, the electrons will be located away from the nucleus. So, as you go on adding the orbitals, what will happen? The size will go on increasing, right? So, in this case, what will happen? From the nucleus, if the electron is present here, from the nucleus till the electrons, the distance has increased. So, the size, and along with the distance, the size of the atom also increased. That's why principal quantum number, as it increases, the size of the orbit also increases. And it also ensures that the electron is moving away from the, or it is located away from the nucleus. Since energy is required in shifting away the negatively charged electron from the positively charged nucleus, the energy of the orbital will increase with increase in n. Now, this increase will also increase the, but it will increase since energy is required in shifting away the negatively charged electrons from the positively charged nucleus. Now, from here, we have to shift these electrons here. This shifting requires energy, yes or no? Now, that energy of the orbital will increase with increasing n, that is the principal quantum number. And next is the azimuthal quantum number, that is L, is also known as the orbital angular momentum or subsidiary quantum number. These are the other names for azimuthal quantum number, and it is denoted as small l. It defines the three-dimensional shape of the orbital. Now, principal quantum number basically deals with the size and the energy of the atom. Now, azimuthal quantum number, it deals with the, or it defines the dimensional shape of the orbital. For a given value of NL can have n values ranging from 0 to n minus 1. That is, for a given value of n, the possible value of L is 0, 1, 2, 3. So the value of L can start from 0, 1, 2, 3. It can start from 0 or n minus 1. For example, when n equals 1, okay, value of L is only 0. Why value of L is 0? Because value of L can be calculated by n minus 1. N minus 1, whatever value you get. N is your principal quantum number, right? So principal quantum number minus 1 will give you the azimuthal quantum number. Okay. Now here when your n equals 1, so 1 minus 1 will get a 0 for you, right? The answer will be 0. So the value of L is only 0. For n equals 2, the possible value of L can be 0 and 1, right? You can get 0 also, you can get 1 also. For n equals 3, the possible value will be 0, 1 and 2. Okay. So each shell consists of one or more subshells or sublevels. Okay. Now the number of subshells in a principal shell is equal to the value of n. For example, in the first shell, n equals 1, there is only one subshell which corresponds to L equals 0. There are two subshells, L equals 0 and 1 in the second shell. Now n equals 2, 3, L is equal to 0, 1, 2 in the third shell where n equals 3. Now the subshells increases with your number of principal quantum numbers. So if your principal quantum number is 3, that means you have 0, 1, 2. So n is 3, you have 3 subshells, 0, 1 and 2. When n equals 2, you will have 2 subshells, that is 0 and 1. When n equals 1, you have only one subshell, that is 0. Okay, where L equals 0. L basically tells you the number of subshells that you will have. Okay. And this will continue. So each subshell is assigned by an azimuthal quantum number L. as I told you. Now, subshells corresponding to different values of L represented by the following symbols. Okay. Now, the subshells are represented by the symbols. Value for L starts from 0, right? 0, 1, 2, 3, 4. And the notation is S, P, D, F, G, H, and so on. For principal quantum number, it is KLMN. Here it will, that is the main shell. Now, these are the subshells. Okay? That is the principal shell. And then we have the subshells. Now, this is the principal shell, that is 1. When n minus, now how you calculate L? L is calculated n minus 1. So 1 minus 1 is 0. So we have 1s shell. Because subshell only 1 is there, right? So you denote it as S, P and D. So 0 means S. So 1s. 1s why? Because it is 1. Okay. Now when you have principal number 2, okay, again you will have 0. So it will be 2s. Then you have 1. What is the answer? 2 minus 1. You get 1. So you will have 0 and 1. 2 orbits, right? 2 subshells. So 2, 0, 2, 1. So it will be 2s, 2p. Because 1 stands for p, right? Now 3 will have 3. 0, 1 and 2. So it will be 3s, 3p, 3d. 4 will have 4. 0, 1, 2 and 3. Well, 4 has 4p, 4d, 4n. So similarly, it will continue. Next is the magnetic orbital quantum number, that is MI. Gives information about the spatial orientation of the orbital with respect to standard set of coordinate axes. Now this gives you the spatial orientation. Now this is how a 3D orientation graph. This will be your atom. Now, in which direction it is orienting? In this direction or in this direction? Whichever direction it is orienting, it is moving. That particular thing is given by the magnetic orbital quantum number with the standard set of coordinates. Okay, so these are coordinates, right? X coordinate, Y coordinate, X coordinate, Z coordinates. With respect to these coordinates, it is given. For any subshell defined by L value, 2L plus 1 value gives your magnetic quantum number. Okay, now how you will get a magnetic quantum? How you get the principal number is the number of atoms, right? That is n. How you get the azimuthal quantum number? It is n minus 1 equals L. Now, how you will get the magnetic quantum number? Magnetic quantum number, the formula is 2L plus 1, which gives you the magnetic quantum number. Okay. Now, magnetic quantum number, you will have minus L minus 1 minus L minus 2. This will continue. This starts from the y coordinate. This is an x coordinate where you have a 0, and this is the minus section. This is the plus section. Okay. So this is the coordinates. Thus, for L equals 0, the only permitted value of M1 or magnetic or quantum number is 0, because anything multiplied for 0, it will be 1. So the 1 is orbital. For L equals 1, it can be minus 1, 0 and plus 1. So that is 3. There is p orbitals. For L equals 2, it will be minus 2, minus 1, 0, plus 1 and plus 2. All the negative and positive coordinates you have to take. So 5 orbitals, that is your d orbital. Now you know that S, P and D you have, right? Now S has 1, P has 3 and D has 5. is how it looks. Now, why do they have this is because for L equals 0, permitted value of M is, by calculating, you are getting 1, right? There is only 1. So that's why it is 1 here. Now for L equals 1, magnetic this will be -1, 0, +1. So -1, 0, +1. That is P. Okay. For L equals 3, it will be 2 multiplied by 3 plus 1. Now 2 multiplied by 3, wait, I'll take an example of L equals 2. Now 2 twos are 4 plus 1 equals 5. So total 5. 5 means you will have 0, this is 1, plus 1 plus minus 1, 1, 2, 3, plus 2 minus 2, right? So you will have coordinates like this. You will have 0 because you are getting an answer of 5. So you should have 5. So you will be plus 1 plus 2, minus 1 minus 2. So 1, 2, 3, 4, 5. So D will have 5 orbitals. This one will be -2, -1, 0, +1, +2. So this is how the orbitals are given. It should be noted that the values of M1 are derived from L and the values of L are derived from N. As I told you here, right? L is derived from N and M is derived from L. So they are interconnected with each other. Now each orbital in an atom therefore is defined as the set of values of N, L, and N. So everything in atom, it is basically given because of all these three numbers. So an orbital described by the quantum numbers n equals 2, L equals 1, M equals 0 is an orbit of p subshell of the second shell. The following chart gives the relation between the subshells and the numbers of orbitals associated with them. So these are the value of L, okay, and the number of orbitals and notations of subshells. Now, electron spin s. The three quantum numbers labeling an atomic orbital can be used equally well to define its energy, shape, and orientation. But all these quantum numbers are not enough to explain the line spectra observed in the case of multi-electron atoms. That is, some of the lines actually occur in doublets, two lines closely spaced, triplets, three lines closely spaced, etc. Now, the three quantum numbers labeling an atomic orbital can be used equally well to define its energy, shape, and orientation. Right? You can use all these three to define their energy, state, and orientation because number of principal number deals with the energy and that size. Azimuthal number deals with their shape, how far, how long, how close, and orientation is basically dealt by the magnetic quantum number. But all these quantum numbers are not enough to explain the line spectra observed in case of multi-electron atoms. They were not able to explain the line spectra, right? I showed you the line spectra for hydrogen. The same line spectra wasn't able to explain by the quantum numbers, mainly of the multi-electron atoms. Now, this suggests the presence of a few more energy levels than predicted by the three quantum numbers. Apart from whatever these three quantum numbers predicted, the energy levels, there are some other energy levels which were not able to be explained by these quantum numbers. So, George Uhlenbeck and Samuel Goudsmit proposed the presence of the fourth quantum number, that is electron spin quantum number, that is MS. Now, all these three weren't able to explain about the energy levels, right? So these two scientists, they gave a fourth quantum number, that is electron spin quantum number. An electron spins around its own axis much in a similar way as Earth spins around its own axis while revolving around the sun. And they said that an electron, it spins around its own axis. How Earth spins around its own axis? Similarly, the electrons also spin around the own axis. Okay. Now, in other words, an electron has, besides charge and mass, intrinsic spin angular momentum number. Now, electron, along with the charge and its mass, it also has a spin, angular spin. Now, spin angular momentum of electron is a vector quantity. Okay, can have two orientations relative to the chosen axis. It can have two orientations in the chosen axis. These two orientations are distinguished by the spin quantum numbers. Now, they can rotate in a clockwise or an anti-clockwise manner. Now, these are distinguished by the spin quantum number, and the values which are given is plus half and minus half. Plus half or minus half depending on their orientation of spin. Now, these are called two spin states of the electron. These plus half and minus half are known as two spin states of the electrons and are normally represented by two arrows, that is spin up. They can spin from up to down, or spin down. Spin down means they can go from down to up. Okay, so these are two things. So two electrons that have different uh, spin quantum number values, one is plus half and other is minus half, are said to have opposite spins. Okay, so plus half and minus half means they are opposite spins, right? So electrons that have and two electrons together, when they are there and together, they means each of them have a opposite spins. So an orbital cannot hold more than two electrons, and these two electrons should have opposite spin. So an orbit, it cannot take more than two electrons. It can only take two electrons, and these two electrons should have a opposite spin. If one is from upside down, then the other one should be down up. Okay, so they should have a opposite spins. Now, to sum up the four quantum numbers, provide the following information. Okay, when you take all the four together, it gives you this information. First, n defines the shell. So principal quantum number defines the shell, determines the size of the shell, size of the orbital, and also the energy of the orbital. This is what principal quantum number gives. There are n subshells in the nth shell. That is, there are various subshells with one shell, right? So that is given by the azimuthal quantum number. So you identify the subshells and determine the shape of the orbital using the azimuthal quantum number. Then the shape, now there are 2l plus 1 orbitals of each type in a subshell. That is 1s orbital where L equals 0, 3p orbitals where L equals 1, and 5p orbitals where L equals 2 per shell. Okay, I told you, right? When you calculate this with the formula, you can get in s orbital you get 0, in p orbitals you get 1, and in d orbitals you get, s orbital is calculated using 0, p orbital is calculated using 1, and d orbital is calculated using 2, where you have to substitute the L values 0, 1 and 2 in this formula. Okay, that will give you the number of subshells present in the principal shell. So to some extent, L also determines the energy of the orbitals in a multi-electron atom. Next is your magnetic spin. What is a magnetic spin? It designates the orientation of the orbital. It gives you the orientation of the orbital, how it orients. For a given value L, M has 2L plus 1 values. So the same as the number of orbitals per shell. It means that the number of orbitals is equal to the number of ways in which they can orient. So it is said that the number of subshells is equal to the number of ways in which they can orient. Okay. The next is the spin quantum number, refers to the orientation of the spin of the electron. So this is what we have seen today. In our next class, we'll see the shape of the atomic orbitals and the filling of this atomic orbitals, even the energies of the orbitals. So thank you for watching my video. Please do like, share and subscribe to our channel.